what I mean by scams are the Wine Lab is another one of those classic is one of those classic ones that I love where it's a lot harder until you actually sit down and think about it. So the Wine Lab, once you figure out what you need to do, which is you want to take a look at once you validate, which is fairly straightforward, or you can skip the validation process until later because you can just write that as a function. Once you do that, basically you'll want to create a dictionary to represent those double vowels, like EI to A, the A sound, or or AI to I. IE, I think. I'm not sure. Now with single vowels, you don't have to worry about that. What you're going to do is you're going to go ahead, have a while loop. Look at your, and what you want to do is basically you'll want a while loop because you don't know how many characters you're going to be reading. What you're going to do is say, I'm at index whatever. Let's take a look at the slice that contains me and the next letter. Okay. And why a slice? Well, because if you're at the end, if you slice out of range, it's not going to hurt. So basically you say, hey, are these two letters, me and the next guy, are we in the dictionary of double vowels? If so, great. I can translate that immediately. Otherwise, if they're not in the single vowels, then, sorry, in the double vowels, check to see if I'm a vowel. And if so, translate the vowel. And otherwise, if it's a consonant, translate it into a consonant. If you are in the double vowels, you move forward two indices. If you're a single letter, you move forward one indice and you check them and you just continue until you hit the end. That's it. You're not rebuilding a string. You should have your input word, and then you should return an output. So you're building from a new empty string. You're going to be appending and accumulating to a string. Yeah, you should have two strings, one which is your original word and the other one which is your output. And you want that out, and the reason you can't use replace is not that you can't use it per se, not that you cannot use that function, but if you try to use it, it's going to cause more trouble than it's worth, because when you replace certain letters, you're going to have to replace other, that creates more letters, which could be replaced by later operations. So it's not really super bad. If people are still having trouble on Thursday, I'll try to cover it some more. So it's one of those where the dictionaries make it simpler. If you're not super comfortable about doing dictionaries, it becomes a while loop with a bunch of if statements in it, and basically saying, am I going forward two characters or one character? Am I in a one character scenario or a two character scenario? All right. So let's go ahead and talk about so this class actually happens to be, this lecture specifically happens to be one of my favorite lectures because we get to talk about really mind-blowing, mind-straining stuff. Also, I don't like working hard, and Monte Carlo approximations are all about not liking to work hard. Because it says, ew, this math looks difficult. Probability, oh God. I don't know what to account for. Are these dependent, independent? Oh no. So instead what Monte Carlo approximations do, as we'll see, is just simply say, we're going to simulate it. And I'll explain those. How many of you had the opportunity to watch the two videos I posted? If you haven't, that's fine. I'm going to go under the assumption that you've been all too busy to watch. Yeah, there were two videos. Don't worry. I'm going under the assumption they're too short. I didn't do the videos. One is from Numberphile, and one is from this guy who uses marbles to simulate stuff. It was a really cool video, I thought of them. So one is explaining the Monty Hall problem, which I'm going to go over today, and one is and one is about Monte Carlo approximations. Now, if I could figure out how to throw Monty Python here, other than the fact that that Python is named after Monty Python, I'd feel like $1 million. So, all right. So what is the Monty Hall problem? Let's start with this problem first, okay? Because I like this problem because it's paradoxical. It's super unintuitive, unless you really know your statistics. And I think we're going to get into quite a bit of argument about it because of how unintuitive it is. And I say that in a great way. So, all right, so let's go ahead and I will go ahead and let's see, share screen. And we're going to share a whiteboard. So the Monty Hall problem, some backstory. This was actually some controversy a while ago. So Monty, I'm just going to Google for a second so I make sure I get the names right, but I believe it's Vos Savant. So there's this magazine called Parade Magazine. And let's see. So I'm going to go ahead and actually switch what I'm sharing. And then I'll go back to that. So we had so it became famous. So the Monty Hall problem became famous after reader is letter quoted in Marilyn Vos Savant's Ask Marilyn column in Parade Magazine 1990. I'll go ahead and just simply say, without getting into the problem, that Vos Savant put out an answer. And many people refused to believe Vos Savant. Vos Savant, by the way, has a lot of stuff. She had a column. She had a fairly high IQ from fairly high, some ridiculously high IQ. So Savant sees IQ tests as measurements of mental abilities and thinks intelligence has so many factors that attempts to measure it are meaningless. So, but anyway, she had a column after she got into the Guinness Book of World Records. But this was possibly the most controversial one because she had an answer, as she gave an explanation about this problem, and then about 10,000 people wrote into the magazine, including 1,000 with PhDs, most of them claiming that she was wrong. Now, even when given explanations, simulations, formal mathematical proofs, many people did not accept that switching was the best strategy. Paul Erdos, one of the most prolific mathematicians in history, remained unconvinced until he was shown a computer simulation. So that is what we are going to do today. We are going to convince you with computer simulation. Paul Erdos, by the way, when they say he's most prolific, you know the 6 degrees to Kevin Bacon kind of thing that people do, right? Well, Paul Erdos is that for mathematicians. They are literally an Erdos number, the number of steps between you and collaborators to Paul Erdos. My Erdos number is 5, meaning that there are 5 steps between me and co-authors to Erdos. That means I published with someone with an Erdos number of 4. So anyway, so let's go ahead and see. Now, I'm not saying that possibly the reason that that Vos Savant got such a huge backlash was sexism, but considering that that this had been solved in multiple papers beforehand, and that it had been this had been shown a good number of times, might have had something to do with it, in my opinion. But anyway, but part of it is also just that the problem is so unintuitive. So we're on a game show called Monty Hall's Let's Make a Deal. It's named after that. And the idea here is that there are two prizes you can get. One desirable, one undesirable. We're going to assume that the desirable prize is a car, okay, because who doesn't want a new car? And the undesirable prize is a goat. Right, I don't know, right? We love goats, but we're assuming that the goat is undesirable here, So anyway, given a choice of 3 doors. So you've got 3 doors. Behind one door is a car. Behind the others, goats. You pick a door, number 1, and the host goes, oh, and the host, who knows behind what's on the other doors. Opens another door, say number 3, and says, here's a goat. Now, do you want to switch? My wife is on your side. She just yelled, "Can I switch to door number 3?" Right. So, anyway, the idea here is it in your advantage to switch? If you want the car, is it in your advantage to switch? Or do you want to stay? Right. So the idea here is like, should you stay? Should you switch? And it's actually, all right, let's just going to be a car and goat. Otherwise it's going to mess with my, groove here. All right. So we've got, so suppose you're on a game show, you've got 3 doors. We pick one. The host reveals a goat in one of the unpicked doors, and he says, do you want to switch? And the question is it in your advantage to switch? And the probabilities say you have that if you stay, you have a 1/3 chance of winning, but if you switch, you have a 2/3 chance of winning. And if that sounds weird to you, you are not alone, right? So let's go ahead and draw this out to show you. But what we're going to do is that we're going to show you is rather than try to do a complex mathematical proof, first I'm going to use art, but then rather than doing a complex mathematical proof, I'm going to use what's called a Monte Carlo approximation to show you this, which is that math is boring, but if we play this game a bunch of times, then we should be able to see what happens. So we'll actually literally play the game and have the computer play the game multiple times so that we can see that. All right, so we've got door 1, 2, 3, right? 1, 2, 3. If we pick a door, so let's say we pick door number 1, right? And our guy reveals a goat. Monty Hall reveals a goat. So is it in our advantage to stay or switch? Well, let's take a look at our scenarios. So scenarios are basically that if there was a goat here, then our configurations are either, well, you think maybe it's 50-50 because that means there's either a goat here or a car here, right? Or it could be a car, a goat, or a car here. But really what it is that we have 3 possibilities. We have car, goat, goat. We have goat, car, goat. And we have goat, goat, car. So if we pick one, right, if we pick this door, basically Monty Hall is going to reveal either this door or this door. Okay? So let's go ahead and assume that so here's our, actually, if I recall, there's a drawing on Wikipedia. God, I love Wikipedia. Why should I settle for my crappy drawing when I can just use one from Wikipedia, right? All right, so here's the initial configurations of the game, right? So here's your choice. You pick this door, and you pick the goat initially. If you switch, you win. Pick the first door again, right? So see, it's goat, goat, car. Pick the first door again. Again, you switch and win. But if you pick the car, the only way you can win is by staying. So let's take a look at this in detail. The idea here is that basically if we go, so the end result of it being an advantage is that you only lose if you initially picked a car, if you switch, right? If the configuration is goat, 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 car, right? If this is the initial configuration, let's say we always pick door number 1 as our first move, okay? Because it really doesn't matter what door we pick. We can always rearrange the doors so that the door we pick is door number 1, right? We can consider door number 3 to be door number 1 and then we can always wrap around the doors. It doesn't matter. Okay, so the door we pick is always going to be door number 1. So if we go with goat car, right? Monty Hall will reveal this. So let's look at our possibilities. If we switch, we win the car. Okay. If we stay still, we lose. All right. Now let's look at the configuration of goat car goat. Right. Again, if we pick door number 1, Monty will reveal the goat. If we switch, we win. If we stay put, we get if we switch, we get the car. If we stay put, we get the goat. And finally, let's look at the last configuration, which would be car goat goat. If we pick this guy, Monty reveals either of the goats. It doesn't really matter, right? So the idea here is we pick this. So if we switch, we get a goat. But if we stay still, we get a car. So in 2 of the cases, staying still gave us the advantage. And in 1 of the cases, if we stay still, if we stay still, we lost twice and won once. If we switch, we won twice and lost once. So it's a 2/3 chance of winning. Now, this may seem really weird but it's all based on the fact that basically Monty's going to reveal a goat to you. If you have more questions, watch the video. My personal favorite example is, well, what if we have like an infinite number of, what if we have like 100,000 doors, right? We pick 1, okay? We have 100,000 doors. We pick 1, and Monty opens up 100,000 doors. So Monty then opens up 99,998 doors to reveal 99,998 goats. And now you're left with 2 doors. Do you switch or you stay still? Right? Because in that case, it's pretty easy to see. Well, if I switch, I'd be banking that my original guess was right. My initial 1 in 10,000 guess was right. So that's what you're doing. And basically when you choose to stay, you are banking that your initial 1 in however many doors chance there was right. Now, this may not seem right to you. I mean, again, and if that's okay, take solace. This guy, mathematical genius, huge thing. How many papers did he freaking publish? 1,500 mathematical papers. Was not convinced until he saw a computer simulation. Okay? So if you feel confused by that, mathematical geniuses were confused by this. Okay? So, And part of it is also the postulation of the problem. Okay, because there's these assumptions about the host must always open a door that was not picked by the contestant. The host must always open a door to reveal a goat and never the car, and you must be offered the chance to switch. Those are the rule, those conditions, essentially. So let's go ahead and simulate this. So what we're going to write is something called a Monte Carlo simulation, which is completely coincidental that they start with Monty. It's just a wonderful coincidence, I believe. So Monte Carlo, for those of you who do not know, right, and this actually gets me to talk about one of those things that really interests me. Monte Carlo. Now, Monte Carlo is in the Principality of Monaco. So I'm going to share my screen and just kind of show you. Because we often think of these countries as these really big things, but that's not always the case. Monaco is a tiny country. Right? So this is Monte Carlo. It's right here. Fairly nice, or fairly close to nice, I should say. That's a joke. But here, Monaco is just a tiny little country over here. Okay. And by the way, and again, like this is one of those microstates that you get in Europe, like Liechtenstein and let's see, Andorra, right? Little country, probably didn't even know it was right here. Let's see, I believe that's Andorra. Andorra. Andorra, in the tiny independent principality between France and Spain. Amazing that there's just these tiny little countries that sometimes exist thanks to the fragmented nature of European history. So anyway, so Monte Carlo is, so Monaco has this small city in it called Monte Carlo, which is very well known for its gambling and casinos. Okay, and again, this is relevant because gambling kind of was the birth of statistics, right? A lot of mathematicians and scientists got high in statistics. You find out like a lot of statistical studies started because mathematicians got hired by gamblers who wanted to figure out what they were doing. So you know, and they Menachem says John Law. I'm really pretty terrible at names right here, so let me go ahead and wiki that. Economist. Let's see. Oh, Law was a gambler. As a gambler, would win card games by mentally calculating the odds. So, yeah, I think Newton also did that because Newton did freaking everything. Anyway. But anyway, doing a Monte Carlo approximation is basically, say you're watching this gambling game at Monte Carlo, you're watching this game at Monte Carlo Casino, and you want to know what the odds are, right? You won't know. Well, it's a complex game. So instead of like trying to figure out the odds by like doing math and stuff like that, instead just count the observations, like on a roulette wheel, right? See, you basically watch the roulette wheel and see how often each outcome comes up and just keep tally of that. And after enough times, you are going to get basically something that approximates the actual odds, right? So the idea here is basically we are taking samples. We are taking scientific samples by observing something, and then after enough outcomes, we should be able to see this happen. So that's what we're going to do with the Monte Carlo method to do the Monty Hall problem. And so what we're going to be doing later with this is we're going to be seeing how this applies to basically scams, which is really fun because a lot of scams, they're structured in ways that seem like you're going to win, but you're not going to win because it's a scam. So what we're going to do is we're going to go ahead and I'm going to create Monty.py and I'm going to share my screen. So let's go ahead and do that. Share screen. Share screen. Okay, so what we're going to do is basically we are going to first make a number, I'm going to make a big global variable called trials. All right. And I'm going to basically, this is how many times we're going to run the game. Now, this should be no problem for any modern computer doing 10,000 trials of anything because it's pretty straightforward. We are going to basically, and now what we're going to do is basically we're going to create a, I'm going to create a function called Monty Hall, and all it's going to do is simulate a single Monty Hall game, a single game of Monty Hall. And we're going to basically create a strategy, and we're going to use, I cannot turn on the keyboard right now, but we'll play with the music after class, Laser. So we're going to basically create a Boolean over here that says, let's see, switch. Let's see, yeah, we're going to call it switch. I was just confused about the coloring. And basically, we'll be able to see. We're going to change our strategy based off of whether or not we switch or not. So
it's working.
It's just not plugged in, Laser.
Oh, I can.
No, don't plug it in.
I can.
Oh. All right. So what we're going to do is now we are going to basically we got to randomly create our our doors. So doors are equal to we're going to go ahead and create instead of going after much suggestion from the class, I think we will go with goat being the good outcome and spotted lanternfly being the bad being the bad outcome. Right, so behind two doors, there's going to be a spotted lanternfly, and behind one door is going to be a goat. Okay, so now what we're going to do is that we are going to shuffle these. So I'm going to have to import random because that will really help us. So because what we're going to do is, I believe that random has a random dot shuffle method. Yeah, random dot shuffle. And what that's going to do is that's going to say, that's going to go ahead and take that, and let's see, it doesn't return anything. Yeah. So let's go ahead and just test it to make Laser, you're making a bit too much noise. So let's go ahead and test this just to make sure. So list range 0 through 10. So basically we'll create a list 0 up to including 9, random dot shuffle. Okay, and we are going to go ahead and shift enter random, right? I'm just basically running just these two lines together, which is a really cool feature you can do. So random dot shuffle, and now, okay, so I actually have to give it a name. So let's go ahead and call it L is equal to, I'm just testing this to make sure that it works the way I think it does. What's the invalid syntax? Oh, okay. Okay, so let's go ahead and do this. Random dot shuffle L. So now if we do L, we see basically that L gives us a completely random output. We run this again, random dot shuffle L, we see that we get a completely different output. So it does change the list. So that's all I wanted to do. So basically it does shuffle it. You don't have to do any assignment. So this will shuffle it so that we've got the goat will get randomly placed in the spot. Spotted lanternfly will get placed. So now we shuffle. Okay. So what we're going to do here is basically we are going to say, hey, so let's go ahead and now let's take a look at the doors. So our choice is going to be equal to, now Monty will know our choice. So our choice is going to be doors 0, door number 0. And if choice equal to a, so if our choice is equal to a spotted lanternfly. Okay, so first, actually, no. So let's look at the things. So goat is at index 0, goat is at index 1, goat is at index 2. So first off, if we choose a spotted lanternfly, actually we'll do with goat is if our choice is equal to the goat first. So choice, goat at index 0, L if choice equal spotted lantern fly and goat and doors 1 equal goat. Okay. So 3 choices there. And I'm going to pass, and pass. So basically what we've got here are 3 possibilities. Right, there are 3 possible arrangements of these guys. So we have our first choice is that goat is at index 0. Otherwise, goat is at index 1. Otherwise, goat is at index 2. So let's go ahead and work backwards. If goat is at index 2, that means our choice was a spotted lanternfly. So that means we're going to reveal that Monty would reveal the other spotted lanternfly. Okay, so that means basically, so we reveal, but we're going to do that silently. Reveal door doors 1, basically, and now basically we would have to ask ourselves if we switch. If switch, so if we switch, then we win. So I'm going to return true to represent that we won. Okay. Else, false. And then I'm going to, and it's really the same over here, right? If we end up with a spotted lanternfly and our strategy is to switch, return true, otherwise return false. And finally, if goat is at index 0, we can reveal either of the doors and we'd be switching to a spotted lanternfly. So if switch equals false, sorry, if switch is true, return false because we'd be switching away from our goat to a spotted lanternfly. And again, this is representing this method. Is goat
now the desired outcome?
Yes, goat is now the desired outcome.
Awesome.
My wife approves. Else, return true, because if we're staying put, then we get our goat. Okay, so again, goat at index 0. If we switch away from it, we're going to lose. And this function represents just a single game. And true representing we'd win, false representing if we lose. Okay, so now this is how a Monty Hall approximation works. I'm going to basically say there's 2 outcomes, winning and losing. Since there's only 2 outcomes, I only need to keep track of 1 because we know the total number of games. We can get the number of losses by subtracting the number of wins from the number of trials. Wins will keep track of the number of times we win, and all we have to do is say for I in, or for blank in range trials, because that's how many times we want to run it, right? So, and the reason we're going to just keep that as a big variable is because that way I don't have to write 100,000 a bunch of times, or if I run this again and again. Actually, I'm going to start it out pretty low and just kind of show you what happens as we get it larger. So trials. So however many games we play, let's go ahead and say result is equal to Monty Hall. So we're going to do Monty Hall, and we're going to say switch is equal to true. That's our strategy. And then if result wins wins plus equals 1. So we increment wins by 1. Else wins plus, otherwise we don't do anything because we aren't keeping track of losses because we don't need to. And now once we're done, we're going to just simply print, we're going to not, instead of printing the number of wins we have, we'll just print out the percentage. Wins is equal to wins divided by trials. That's going to give us a number less than 1. But if we want actually a percentage, that's pretty easy to do. We'll just simply say multiply u by 100 and give me a % sign attached to that. So let's go ahead and run this. And with 10 things, we run 90%. With 10 runs, we won 90% of the time, right? We just simulated 10 games. Then 50%. Oh, that's a bit of a swing. That's not too accurate, right? So the idea here is that we run this and we get a huge number of swing, right? So what we're going to do is that we are going to increase the number of times we run this game. And boom, we went up to 10,000 from 10, and it still ran very quickly. And it says 66.2. If we go to 1,000, we actually see that we'll get around 66.3, 66.7, right? But the more trials we do in a Monty Hall approximation, and there it actually made my computer do some number crunching. Yes, you can do that number crunching, that comma thing. It's kind of useful sometimes to do that way, but notice that it created a space automatically for me, which I didn't really need or want. But notice that as we increase the number of trials, by the way, we went up to 1 million trials here. and took a bit of time to do a million trials, right? Now notice that basically if I do yet multiply, if I go up another factor of 10, it will take 10 times longer to run because I'm doing 10 times as many trials. See, still going, but it will end, don't worry. But this is what a Monte Carlo approximation is. Eventually, we get it so that the accuracy is very good. That's the goal of a Monte Carlo approximation. Basically, we didn't have to actually do any of the math. We just simply simulated our outcomes until we got an accurate result, until our result was fairly solid and unchanging. So that's a very useful tool. Excuse me. Okay. So now you can kind of see where this goes. Now, I'm not going to do all these in class, but let's go ahead and just pull up the, now let's go ahead and pull up our, the project that I linked to, because this kind of went away from the way I was going to do the project, but whatever, because it's still useful for you to do. This is essentially your exercises and stuff and readings for the week over here. Doing this, the Monte Carlo simulations. Approximating pi is a bit more abstract, but you can approximate pi with a Monte Carlo simulation as well. It's kind of insane. I'll show you that in a bit, and I'll work on that in a bit. Another thing they show you is that you can actually use, do like things like predicting stock prices to figure out with Monte Carlo simulations, basically randomly, like trying to randomly guess what things are going to be. It's pretty cool. And right over here, we see the Monte Hall approximation as well. But let's go ahead and talk about approximating pi. Approximating pi is one of those classic Monte Carlo simulations that has no kind of, that really is boring, to be honest. So actually, give me 1 sec. I might completely scratch this and say, do this for homework, because I think you might be much more entertained by doing something, more fun. Let's see. So documents, is it in here? How to cheat. I'm a horrible influence on people. Okay. How to cheat at everything. Ah, yes. Now, so let's go ahead and see. All right. You know what? I'll start with the approximating pi, and I'm going to leave the scams for Thursday. That seems like a lot of fun. That seems like the best thing. So so first off, pi, as I think I've discussed earlier, is this irrational number, meaning you shouldn't argue with it. But no, meaning that it cannot be represented as a fraction. It means that basically that we don't really have an easy way to represent it other than using a symbol. We can have fractions that are approximations, right? Like 300 and so 355 divided by 113. So it might be hard to see here, but 355. Yes, 355 divided by 115. Or 113 gives us 3.14159. That's actually, but it's pretty accurate for, you know, just a little bit for a pretty good, you know, it's pretty good for just approximating stuff. Now they said they were able, so someone at Google announced that they were able to compute 31.4 trillion digits of pi using the Y cruncher in Google Cloud. It took 121 days to complete. These are basically different ways and formulas of approximating it. But another way to do it is what's called the dartboard method, which is suppose we have, let's see, give me 1 sec to, where'd my pen go? Because this is one that really, you can list it out, what needs to happen. But honestly, unless you draw it, it's kind of impossible to figure out what's going on. And of course, I had the pen and then I misplaced it. Yeah, really showing that you're a competent adult here, Professor Rosen. All right. All right, give me 1 sec. I swear. Because normally it's the pad I can't find. But the pen. Let's see. And I don't think I can blame this on a rambunctious toddler. I had the pen. Oh, there it is. It just got knocked to the floor. The pen is behind one of 3 doors. Excellent. Okay. All right. So essentially what we're going to do, the whiteboard method, so the dartboard method basically says, how can we approximate pi? Now, first off, what is pi? Like, what does it actually represent? What, not as a 3.14, but what is it? What does pi represent in terms of a value? What is it telling us about a circle? It's a ratio, right? What is the ratio of? It's not a trick question here. The ratio of the diameter to the circumference, right? So the diameter of the circle is equal to, pi times the diameter is equal to the circumference, right? So, or as you might otherwise see it, it's 2 pi r is equal to the circumference, if you remember that formula. But right now I'm going to use the diameter because that's a bit easier for us. Pi is the ratio between the diameter and the circumference. So let's go ahead and draw this kind of, I'm going to go ahead and try to draw this weird kind of dartboard, which is that I've got a square here, and inside of it, I've got a circle circumscribed in it. So now note that the diameter of this circle over here, d, the diameter of the circle is equal to the side length, okay? Note that basically that the length of one side of the square is equal to the diameter of the circle, okay? So, so what would the area of this circle be, and what is the area of the square? Well, the area of the square is d squared, okay? And we know that's bigger than the circle, right? We know that's bigger than the circle. What is the area of the circle? Area of the circle, right, is pi r squared, or in other words, what? In terms of d, pi d over 2 squared. Right, not in typical way you see it, but you see that it is. Now, what we can do is that we know that this square is bigger just because, right, the circle fits inside the square, okay? And basically, let's go ahead and just kind of, let's go ahead and just simply, let's go look at expanding this. So pi d squared over 4, right? And if we were to assume that basically that that we had a, we could cancel these and get 1 on each side, which honestly is perfectly fine. And we'd get basically 1 is greater than pi over 4, which is true. But what we could see here is that basically that we can create a dartboard, which is a unit circle centered at 0, 0, and has a radius of 1 over here. So this has a radius of 1, which means this is got an area of, this got a side length of 2. So our dartboard is the middle of a square that is 2 by 2, and there's a magical force field around here that's going to prevent any dart that we throw at this dartboard from landing outside. Very relevant. I really like the relevant image, Muhammad. That is very relevant. So what we're going to do is we're going to simulate randomly throwing darts with a random number generator. We're going to choose some random coordinate between -1 and +1 for the X and the Y's. And then we're going to say, hey, is it inside the circle? And what's cool about this is because the area of the circle is pi r squared, and the area of the unit circle is just pi, the area of the 2 by 2 square that contains our dartboard is, and the area of the dartboard, the area of the square would be 4. So the ratio for the number of darts that hit the dartboard is total. Basically, we can use this to calculate pi over 4. So let's go ahead and show. This is just kind of better to show than to kind of explain. Okay. So let's go ahead and I'm going to import turtle, because why draw things without using it? Okay. The idea here is that we can approximate pi by throwing darts and basically counting the ratio of darts that land inside a circle versus the darts that don't land inside the circle. And that will give us pi over 4. It's actually quite amazing. And honestly, I don't really explain it that well. I think most of you are lost on this, to be honest. But the idea here, so do you want me to go in more detail about this? Or elaborate some more? Okay. So let's go ahead and I'm going to stop share screen. All right. Okay, yeah. I realized that I had kind of hand waved there and that was not good. So, okay, we've got this dartboard. Okay. And what we've got is we've got a circle. Our objective is to figure out what the value of pi is. Also to figure out why I didn't become a medical doctor, because my handwriting and drawing skills are just so bad, you know. But that's an investigation we can do another day. Okay, so we've got this. I'm so bad at this. Okay, we've got this circle over here. This terrible, terrible circle over here. And the idea here is that we've got this circle of radius. Okay, let's go ahead and say this is at location 0, 0, and this is at 0, 1. So in other words, this radius has a length of 1. Okay, this radius has a length of 1, which, by the way, doesn't get us to a corner, but it does get us to the sides over here, right? And since this is a radius and this is a radius length, okay, this is a radius length, this is a radius length, so that means that that this is as long as the diameter and that this is of length total 2. Okay, so this is length 1 over here and the side is 2. So let's go ahead and talk about the area. The area of this square is 2 squared, right? So that would be equal to 4. Not 9, 4. Okay. Now for the radius, for this circle, we know that basically that the area over here is what? It would be pi r squared. Radius is 1, so 1 squared becomes pi, so the entire area of this is pi. Okay, so the area of this is pi, the area of this is 4. And what we can see here is that, that if this is pi, we can kind of like subtract out if we know what the area is, what we can do is that we can like throw random darts at this dartboard, okay? And what we could do is that we could count the number of darts that land inside here versus the number of darts that land outside of the dartboard, right? So inside the circle versus out of the circle, and use those numbers to basically we can to figure out what pi is, right? The idea here is by throwing darts at the dartboard. Basically, we would get number that we'd say that's the number of hits, and the number of hits outside of the so the number of hits that land inside the circle versus the total number of darts that we throw, that would be equal to a number. Now, what is that number going to be? It's not going to be pi, actually. What it's going to be, because what it's going to be is, it's going to be, well, the area might, well, if we throw basically enough darts to cover this entire space, right, we'd be doing 4, we'd be basically subtracting this out. So the total number of darts, well, let's actually think about this. What is the total number of darts going to be? Well, the total number of darts would be if we threw enough darts to cover the entire area, would basically take up an area of 4, right? And so the number of hits, the things that would land inside, would be equal to pi. So the idea here is that the number of darts that we throw inside of this circle over the total number of darts is going to approximate pi over 4. Wait, what's pi? Pi is pi. Pi is the area of the circle here because the circle has a radius of 1. Total is the total number of darts I'm going to throw. It is the square. It is the number of trials we are going to do. So basically, we're going to say, hey, if we do enough trials, we should be able to approximate pi over 4 without actually ever doing any math. We're going to instead just throw darts and count them, or rather, any hard math. Pi over 4 represents pi over 4. It represents the total number of hits.
So,
yeah, go ahead.
Okay, so just to be clear, like, all right, so the way I understand it, like, total is like the total of the area of the side. So, like, no matter where you hit it, it's going to be like the total. And then the hits are like the darts you hit inside the area of the circle.
Right.
Right?
Right.
Okay, I get it. Okay, thank you.
Mm-hmm. Right. And actually, that's an excellent way to put it, Cameron, which is the likeliness it will hit in the circle, right? Which is that our area is, the area of the circle is pi. The overall area of the square is 4. So the ratio of it landing in inside the circle is pi over 4 because we're inside, because the entire area is 4. This is the pi is the area that's cut out of it. So what we're going to do is that we are going to approximate this using turtles because that's because we'll let our turtles handle like the being thrown. So first thing I got to do is set it. So I'm going to do something that we saw in the turtle exercise, which is I'm going to do, let's see. So I need win.set world's coordinates. So let's go ahead and, no, I don't want to actually search for HTTP. I want to search for Python. Win set world coordinates. So we need to do screen set world coordinates, which would be the X coordinate on the lower left. So basically we're saying this is the square. Okay. So let's see. So, and how do I create the window? Let's go ahead and see. How do we create a screen? Let's go ahead and move up. Oh, yeah, I haven't coded anything yet, but thank you for the reminder. So let's go ahead and, so turtle screen. So how do I get the turtle screen? Oh, the function screen. There we go. So let's go ahead and basically say, okay, when is equal to turtle dot screen to get the screen. Save and run. Okay, that works. When dot set world coordinates. And what this is going to do is that basically it's going to basically box in our turtle. We're going to say, hey, the let's see, set world coordinates basically takes in 4 arguments. Lower left, the lower left corner and the upper right corners. So lower left corner, which is, right, think down and to the left, that's going to be -1, -1. So 1, and then the upper left corner of the screen is going to be 1, 1. Make sense? So let's create Bob. Is going to be Bob is equal to turtle dot. So just to show you what that's going to do, turtle dot turtle. Okay. And now we're going to say Bob dot go to 1, 1. And notice now that he's at the upper right corner of the screen, right? So what this did for us was actually really nice. It set it so that we've got this upper right, that basically that this is 1, 1. This is over here, if you can see my mouse, -1, 1. This is 0, 0. This is 1, -1. So basically it set it up to be the unit square, right? This thing has an area. This is exactly the square that I failed at drawing. All right, so now what we've got, so we've got this square. And we could draw the circle. Actually, let's see. Bob dot, how does that work? Bob dot circle 1. Let's see what he does. So he would draw a circle over there. So let's go ahead and say Bob dot pen. We don't need to draw the circle, but I'm going to do it anyway. Pen dot up. Pen up. Bob dot go to. We're going to go ahead and send him to 0, -1, just because it looks like he only draws half the circle if we do that. And then Bob dot pen down. Pen down. And then Bob dot pen up. Bob dot go to 0, 0. Bob dot pen down. And actually, no, we're not gonna, he should never have to, we're never gonna have to use the pen with Bob again, or because what we're gonna do from now on is we're gonna stamp. Okay. So this is what I tried and failed at drawing. Should have started with this. And then drawn on this, but hey, you know, now I know. All right, so what we want to do is basically figure out, so what we're going to do is that we are going to give Bob random coordinates. So for instance, Bob dot go to, and I'm going to need to import random. Import random. Bob dot go to random, and then we want to go somewhere within the screen. So we want to go somewhere where the X range is within 1, 1 and 1. Dot. Next int. Wait, no. That would just give me an integer. That would give me 0, 1 and 1, right? So notice that I've done this plenty of time, or I've done worked with random plenty of times, but I still need to look it up. But I saw that I was making a mistake. because I've made mistakes like this so many times. So let's go ahead and see rand range. So, okay. So that gives me an integer. I don't want an integer. Okay. Randomly selects the range of integer. So let's go ahead and see what will give me a float. Because there will be something that gives me a float. I might have to play with it, but that's okay. Random dot shuffle, random dot uniform returns a random dot floating point between the n such that a is less than. So in other words, it chooses a random point between a and b. The end point may or may not be included depending on how it rounds, and it does it at a random. And you can pretty much guarantee that's going to be a uniform distribution because it says uniform. In other words, everything is equally likely. What were you doing?
I have 3 eyes.
You have 3 eyes? Or what? What are those? They're blocks.
Yes. It's the rectangle.
Mm-hmm.
When the rectangle, we call them eye.
Mm. So random dot uniform -1 1 random dot uniform. So basically he's going to go to a if I tell him this, Bob is going to go to a random spot now. So he went there that time. Let me zoom out a bit. Right? He's going, sometimes he is inside the circle, sometimes he's not inside the circle. Note that basically that the range is -1 to 1. So he's just choosing a random X and Y. Okay. So what we're going to do is that we are going to figure out whether or not he lands inside the circle or not. All right. So how do I tell if he's landed inside the circle? Well, we know, so some math over here. We know that the dart lands in the circle if it's in the distance, if the distance to 0, 0 is less than or equal to 1.0, right? That means basically that it's got to land within less than a radius distance from the circle, right? If it's within a radius distance of the circle, that means it's within the circle, right? The radius here is 1, right? This is greater than a radius because, of course, this circle, the circumference of the circle, it's this space that extends out a full radius length. So the distance is the x coordinate squared plus the y coordinate squared, and then the square root of this. So let's go ahead and basically get, so in this case, let's go ahead and say, let's go ahead and do, let's go ahead and create variables instead. X is equal to this distance. Y is equal to this. Okay. X, Y, go to this, and now let's go ahead and figure out whether it's in this range. So, if x squared plus y squared, and then how do I do the square root? Math dot square root is less than or equal to 1, then it's inside the circle. So let's go ahead and import math. Okay. Now, I'll go ahead and color it blue. What color should we use if it's inside the circle? And what color should we use for outside the circle? Vote now. Purple. Okay, most people seem to. People are going for purple inside. Let's go with purple and blue, some vapor wave. So we're going to go for purple inside. So Bob.color purple. Else Bob.color blue, and I need to put it in quotation marks. I make that mistake all the time, right, too. But again, I've got kind of this mental checklist that goes on over here. So it's purple now because he's inside the circle, blue out on the outside. Red is suspect. Right. All right. So now let's go. So now we see this. But now let's go ahead and, whoops, Control Z. Let's go ahead and indent that and do it a bunch of times. For I in, so all I did was select and hit tab, and now I'm putting in a for loop. For I in range. Let's go ahead and do this 100 times. And so that we get some results, what I'm going to do is I'm going to do, actually I'll do it 10 times because I don't know how slowly it will animate. And when Bob goes somewhere, he's going to go ahead and stamp himself. So he's going to do an inky belly flop onto the page. Here we go. That actually went pretty fast. Let's go ahead and do 1,000 of these. It's going to look like some that are outside are inside and some that are inside are outside, just simply because of the way it isn't exactly pixel perfect. Now though, let's go ahead and remove this. I'm going to remove this circle statement, and then we can kind of see. And then let's see, my turtle.tracer. So I'm not precisely sure what this is going to do, but it says use this to make the animation go faster, which of course I will. So, and my turtle is named Bob here. So, and I removed the circle. So let's go ahead and we see basically that this animation starts. So skips pause. So this says, you can speed it if you use the tracer function. Ordinarily, a turtle draws the picture incrementally every time you perform a drawing operation. For example, a straight line of 100 might be drawn 10 segments with a small pause in between each segment. The tracer skips pause says allows you to say only perform skips updates, only perform every skips update and wait for pause milliseconds. So let's go ahead and try that. So let's go ahead and grab this, move it over here, and okay, turtle says do this at the end, turtle.update, and let's experiment with this speed. So let's go ahead and draw only every 100. Ooh, that went much faster. Okay, we can really speed this up now. And notice that basically we're seeing the... Okay, that's pretty cool, isn't it? We basically were able to draw a circle like that. Just kind of approximating it like that. So now, how good is this approximation? It's actually pretty rubbish as an approximation. Let's go ahead and start counting. Okay, so hits is equal to 0. Now the reason why we use this though is that it's actually as a note, it does it in when we sorry, this is a distributable operation. So if you throw this, I will run it again, just give me a second. If any darts that you throw and hit, if you do them, you can have somebody else do this on their own board, and you can kind of combine results. So this is perfectly distributable. You can do this you can have 10 computers doing this independently, or 100 computers doing this independently, and they all combine the results, and they're going to be an accurate. It'd be as though you had all done this, 10 or 100 times more than you had originally.
What's the buttons on that?
What thing? Oh, you want to push the buttons on that keyboard?
Mm-hmm.
Go ahead. I will share the code. Just give me a bit. Yes. So here, all we need to do is simply put in, so we have trials, and now we'll do hits plus equals 1 over here. And now what we'll do is we will print hits divided by trials. Now, if remember, this is going to give us pi over 4. So I'm going to multiply. I'm going to multiply by 4 here to make it to get it closer to pi. Okay. So let's go ahead and run it. And we'll let it finish. While it's finishing, I'm going to go ahead and share the code. Okay, shared it. It is pretty awesome. Oh no, program exceeded the time limit. So let's go ahead and do 1,000. That should see if it runs fast. Let's see if that runs faster now. As you can see, it's jittering because all this stuff is going over each other. We'll see. I don't know if it's gonna. Trials is not defined. Oh. No, it's not going to happen. You're about to see how horrible of an approximation this is. This is like the worst, one of the worst approximations of pi you can do. But it's great because it shows how to do a Monte Carlo approximation. And we got 3.14064 as our approximation of pi. Which is not ideal considering we ran it for 100,000 runs. Well, it's not good, but I mean, like, I can divide two numbers and get a better approximation. I can divide, what was it? 355 divided by 113. And I get a really good approximation of pi. So, but it's really good for seeing how this does. By the way, if you want to run it for longer, just you can use this command to get it better. So anyway, this is what we have for the. So this is what we have for this. Go ahead and fill these out. If you can't complete them, don't worry. These are going to be graded based on interaction. So in other words, did you try it versus did you get a solution? What do we change? It's on the page. This is what you change to not have it time out. But what I did is that I changed this over here, which basically said only draw every 1,000 steps that we do. Laser sounds like he's hacking into the Pentagon right now. Yeah, he's got my older mechanical keyboard that he's banging on, things like Indestructible. So well, I'll figure out how he can destroy it in just a bit. So let's go and see what we're going to be doing in the upcoming week. For just a second. Let's see. So, here we go. So this was courtesy of my professor, one of my professors here. Let's see, 7-card hustle. So we'll look at this problem tomorrow. Select 5 red cards and 2 black cards from the deck. Shuffle and lay out a line. Let's go ahead and download this rather than. Yeah. So let's go ahead and download this, open it, and I'll share it. Yeah, open it in Word. So we'll be looking at this question in terms of Monte Carlo approximations. Select 5 red cards and 2 black cards from a deck of cards. Shuffle and lay them out in a line. Can you turn over 3 red cards at random without peeking or quietly marking the other cards? This is often introduced as a bet of even odds or better than even odds. Often they'll say, oh, well, so if you flip a card, right, and it's a red card, flip a card, your chance of getting a red card are 5 and 2. Your second red card's 4 and 2. Your third red card is a 3 and 2 chance of getting a red card. So you win if you can select 3 red cards. But what are the real odds of you doing this? He's basically, and the scammer will basically say, oh, you've got an even chance of winning. It's 50-50 or better than 50-50. Look, none of these chances are below 50%. But what are the chances that instead of you winning, the scammer wins? So what we'll do is that we're going to look at games like this, and we're going to try and that games that basically that the odds are presented in one way. But once we simulate the game, we see that the odds are actually not so great for us. There are a number of games that I do know that are actually kind of amusing with regards to this. So we will be seeing these. So, because, you know, I joke about mathematics being boring, but it's really not. It's just hard work. But it's fun when you can kind of see how math can be, you know, how you can be very deceptive with mathematics. I shared the code for the second one. So let me go ahead and share that. I'm going to also stop sharing, but you guys are dismissed from class from today. The only thing I'll mention before you leave is that the assignment I give out for this one called Pig is basically you're going to be doing a Monte Carlo simulation on a dice game called Pig. So I've shared the code, and that the game is actually pretty fun. There's no optimal strategy for it. I would try it on your own. You're going to be graded based off of your interaction on it, not whether or not you were able to complete it. So try it. If you can't finish it, whatever. You'll be graded on whether or not you tried it, though. Okay? So anyway, have a great day. Let me go ahead and end the recording. Shit.